Welcome to Chemistry with Caroline. In this video, we're going to look at an introduction to acids and bases for organic chemistry. And really, this is going to be sort of a review of what you learned in general chemistry, and then we'll adapt it to how we think of acid-base chemistry and the particular aspects that we study in organic chemistry. So we'll start with definitions you're probably familiar with. I'm going to write those on the side here. So we'll start with an Arrhenius acid or an Arrhenius base. So I'm going to have two spots here. We'll make a little table. So here's acids and bases, because we're going to compare to other definitions of acids and bases. So an Arrhenius definition of an acid is something that generates H plus or hydronium ion in solution. Okay, so if you have an acid, it will generate H plus in solution, and really that H plus is usually attached to a water, so we sometimes draw that as H3O plus. You'll see in OChem we use H plus a lot. This is a lazy organic chemist way. So any species that we dissolve in solution and we increase our H plus concentration, that's going to be considered an acid. And in Gen Chem, you probably had a list of like 6 strong acids that dissociate almost completely to really increase the amount of H plus in solution. The Arrhenius definition of a base is something that increases the presence of hydroxide in solution. So in Gen Chem there, you learned 6 or 7 strong bases, and those were all really hydroxide salt derivatives. So you dissolve them in an aqueous solution, you have this high concentration of hydroxide, which is basic. That's a base. A little bit broader definition is a Bronstead-Lowry acid or base. So I'm going to just go down here. This is a hyphenated one. So the Bronstead-Lowry definition of acids and bases really focuses on the proton in particular. So a proton is a hydrogen that has lost an electron. So it's really like just a proton in the nucleus. That's all there is there. So a Bronstead-Lowry acid is a proton donor, so something that gives up or donates a proton. And that's consistent with the Arrhenius definition because the acid would generate more protons in solution. A Bronstead-Lowry base is a proton acceptor. So a species that will accept protons from an acid, right? So an acid and a base react with one another, and the Bronstead-Lowry definition really has to do with the transfer of a proton from one species, an acid, to another, a base. So in organic chemistry, we're particularly interested in how chemical reactions happen, and we use arrows to show the flow of electrons when a chemical reaction is happening. So I'm going to draw a generic representation of an acid-base reaction. So I'm going to use HX as my acid. So the acid, remember, according to Bronstead-Lowry, is a proton donor. Okay, so you can see it's HX. It's going to donate that proton without the electrons, right? Because a proton doesn't have any electrons. It's lost that electron. And then I'm just going to do a generic base. I'm going to do B. And I'm going to put a lone pair of electrons on there, and I'm going to make that negative. This is going to be my base. And the base, remember, is a proton acceptor. And remember that the proton itself is an H plus, and in chemistry opposites attract, so it would need electrons to accept that proton, right? Electrons are negatively charged, a proton is positively charged. And so this would be an acid-base reaction. I'm going to draw equilibrium arrows because almost all acid-base reactions are in equilibrium to some extent. And I'm going to change colors here so that I can draw my arrows. My arrows always start at electrons. The base is the electron donor and the proton acceptor. So I'm going to start my arrow from the lone pair of electrons on the base, and it's going to end at the proton because that's the bond that's being made. Okay, so your arrows should always originate from electrons. And then the base is just accepting a proton. A proton, right, is H plus. There's no electrons associated with it. And so the acid is donating the proton and it's accepting those electrons. So I have another arrow showing me that that bond between H and X is breaking and that those electrons that were a bond are going to go on to X as a lone pair. So if I draw the products that I formed from this reaction, I now have X, and X has a lone pair of electrons because it accepted those when the bond broke, so it's going to be negative. It was neutral. And then B now has a proton on it, right? So that first arrow that I drew, there's this line here, right? That line, and that shows me that bond was made, and that comes from arrow 1. So like, let's say this is 1, there's 1, and then here's 2, right? And the lone pair of electrons on X is shown from arrow 2. So the arrows are like the directions for what's happening. They show us what bonds are broken and made during a chemical reaction, and that's what organic chemistry really studies, is the mechanism of the reaction, how it happens, what electrons move, what bonds are broken, what bonds are made. Now, if we remember back to Gen Chem again, we can think about some relationships. So HX was our acid, X minus is our conjugate base. Remember that every acid has a conjugate base. B minus was my base, and so HB would be the conjugate acid. So this has been sort of a review of acid-base chemistry and then a look at how organic chemists might think about it. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.